For centuries, the moon looked silent, gray, and lifeless. When we look at it from Earth, it seems calm and unchanging. Unlike Earth, it has no thick atmosphere, no oceans, and no strong global magnetic field today. Earth's magnetic field protects life by blocking harmful solar radiation, and it is created deep inside our planet by the movement of liquid iron in the core. But the moon is small, colder, and today it has almost no global magnetic field at all. So scientists once believed the moon never had one. That idea seemed simple and logical. A small body cools quickly. Its core becomes solid. Without moving liquid metal inside, there is no dynamo effect, and without a dynamo, there is no magnetic field. For many years, that explanation was enough. But in the late 1960s and early 1970s, everything changed. When astronauts from the Apollo program traveled to the moon, they brought something extremely important back to Earth. They brought rocks. These were not ordinary rocks. They were pieces of lunar history, untouched by wind or water for billions of years. Scientists carefully studied these samples in laboratories. They measured their age, their chemistry, and their magnetic properties. And that is when the mystery began. Some of these moon rocks were magnetized. That means they carried a magnetic signature frozen inside them. When certain rocks cool from melted lava, tiny metal grains inside them can align with a magnetic field, like tiny compass needles. If a strong magnetic field is present while the rock cools, the rock records that field. This is called remnant magnetization. On Earth, many ancient rocks carry records of Earth's past magnetic field. But finding this in moon rocks was shocking. Because if these lunar rocks were magnetized billions of years ago, that means the moon once had a magnetic field strong enough to magnetize them. Some samples suggested that this ancient lunar magnetic field may have been almost as strong as Earth's field today. That was not expected. The moon is only about 1/4 the diameter of Earth. It has much less mass. Its interior cooled faster. According to simple models, its core should have stopped moving early in its history. So how could it power a strong magnetic field? This question became known as the moon's magnetic field mystery. To understand this mystery, we first need to understand how magnetic fields are created inside planets. On Earth, the magnetic field is produced by what scientists call the geodynamo. Deep beneath the surface, Earth has a solid inner core and a liquid outer core made mostly of iron and nickel. The liquid outer core moves constantly because of heat escaping from the deeper interior. This movement of electrically conducting liquid metal creates electric currents. Those currents generate a magnetic field. As long as the liquid metal keeps moving, the magnetic field continues. Mars once had a magnetic field too. Evidence from orbiters shows that ancient Martian rocks are magnetized. But today, Mars has no global magnetic field, likely because its core cooled and its dynamo stopped. So scientists expected the moon to follow a similar path, but even faster. Smaller bodies lose heat quickly. Less heat means less motion in the core. Less motion means no dynamo. Yet the magnetized lunar rocks told a different story. They suggested that between about 4 billion and 3 billion years ago, the moon had an active magnetic dynamo. That means its core must have been moving in a way strong enough to generate a field. The age of some magnetized rocks points to a time when the moon was still geologically active. During this early period, large volcanic eruptions filled huge basins with dark lava, creating the flat plains we see today, called maria. These maria are visible even from Earth as dark patches on the lunar surface. Many of the magnetized samples came from these volcanic regions. The astronauts from missions like Apollo 11 and Apollo 17 collected basalt rocks formed from cooled lava. When scientists tested them, they found strong magnetic signals locked inside. This was not a small effect. In some cases, the recorded magnetic field strength was estimated to be tens of microteslas, comparable to Earth's present magnetic field. That is powerful for such a small world. So now scientists faced a puzzle. If the moon once had a strong magnetic field, what powered it? And why did it disappear? Was the moon's core larger than expected? Was it hotter? Did it contain lighter elements that kept it liquid longer? Or was some other process involved? The mystery deepened when orbiting spacecraft mapped the moon's surface magnetism. Later missions, including Lunar Prospector, discovered regions of strong crustal magnetism. These are areas where the lunar crust itself is magnetized. Interestingly, these magnetic patches are not evenly spread across the surface. They are stronger in some areas, especially on the far side of the moon. This uneven pattern suggests that the moon's magnetic field may not have been stable or long-lasting like Earth's. It may have changed over time. Some scientists propose that instead of a long-lasting dynamo, maybe the magnetization came from giant asteroid impacts. A huge impact can create plasma and electric currents, possibly generating temporary magnetic fields. Could these impact events magnetize rocks locally? Or was there truly a global magnetic field generated deep inside the moon? To answer that, researchers needed better data, better models, and a deeper understanding of the moon's interior. Seismic instruments left behind by the Apollo astronauts detected moonquakes and gave clues about the moon's internal structure. Data suggested that the moon does have a core, and that part of it may still be molten today. But the core is small, only a few hundred kilometers in radius. That makes sustaining a strong, long-lasting dynamo more difficult. And yet, the magnetic evidence from ancient rocks is hard to ignore. Over the decades, scientists developed new techniques to measure tiny magnetic signals. They carefully ruled out contamination from Earth's magnetic field. They tested whether shock from impacts could create similar signals. Again and again, the results pointed toward an early, active lunar dynamo. So now the question became more detailed. What kind of dynamo could exist inside a small body like the moon? Could tidal forces from Earth play a role? After all, the moon is locked in orbit around Earth, and gravitational forces between the two bodies are strong. Early in the moon's history, it was much closer to Earth. The tidal interaction would have been far more intense. Could that gravitational energy have stirred the moon's core, keeping it moving and generating a magnetic field? This idea opened a new direction of research. The moon's magnetic field mystery is not just about magnetism. It is about heat, gravity, planetary formation, and the deep connection between Earth and its only natural satellite. To understand how the moon could have produced a magnetic field, we must go back to the very beginning, more than 4.5 billion years ago, when the solar system was still young and violent. At that time, planets were still forming, and large objects were constantly colliding. The leading explanation for how the moon formed is called the giant impact hypothesis. According to this idea, a Mars-sized body named Theia collided with the early Earth. The energy of this impact was enormous. Rock was vaporized. Debris was thrown into orbit around Earth. Over time, this hot cloud of molten material came together and formed the moon. This theory explains many things. It explains why the moon has a similar chemical composition to Earth's outer layers. It explains why the moon has a relatively small iron core compared to Earth. Most of the heavy iron likely sank into Earth after the collision, leaving the moon formed mostly from lighter mantle material. Evidence supporting this theory comes from chemical analysis of lunar rocks returned by the Apollo program and studied in laboratories on Earth. These rocks show isotopic similarities between Earth and moon materials that are difficult to explain in other models. If the moon formed from hot molten debris, then early in its history, it was covered by a global ocean of magma. Scientists call this the lunar magma ocean. As this ocean slowly cooled, heavier minerals sank and lighter minerals floated, forming layers inside the moon. This process shaped the lunar crust and mantle. But deep inside, a small iron-rich core also formed. Even though the moon's core is small compared to Earth's, it still contains metal capable of conducting electricity. For a magnetic field to exist, three main conditions are needed. First, there must be a fluid that can conduct electricity, like molten iron. Second, there must be energy to keep that fluid moving. Third, there must be rotation to organize the motion into patterns that create a stable magnetic field. The moon rotates, but very slowly compared to Earth. It completes one rotation every time it orbits Earth, which is about 27 days. This slow rotation makes dynamo generation more difficult. Also, because the moon is small, it loses heat quickly. Heat is the engine that drives convection, which is the movement of hot material rising and cool material sinking. On Earth, heat from radioactive elements and leftover energy from formation keeps the outer core moving. On the moon, scientists believe that heat would escape too quickly for long-term convection to continue. Yet the magnetic rocks tell us that something was moving in the lunar core billions of years ago. So where did the energy come from? One major clue comes from the relationship between Earth and Moon. Today, the Moon is about 384,000 kilometers away from Earth. But billions of years ago, it was much closer. The Moon is slowly moving away from Earth at a rate of about 3.8 centimeters per year. We know this because astronauts placed reflectors on the lunar surface during missions such as Apollo 11, and scientists measure the distance using lasers. If we go back in time, the Moon was much closer, and that means tidal forces were much stronger. Tidal forces are caused by gravity. Earth's gravity pulls more strongly on the near side of the Moon than on the far side. This difference creates stretching and squeezing. Today we see tidal effects mainly in Earth's oceans. But early in the solar system, the gravitational interaction between Earth and Moon was far more intense. Some scientists propose that these strong tidal forces could have deformed the Moon's interior. As the Moon orbited Earth in an elliptical orbit, the gravitational pull would change slightly over time. This changing force could cause the lunar interior to flex. That flexing could create friction and heat inside the core and mantle. Heat alone is not enough. The key is motion. If tidal forces cause the liquid core to slosh or wobble, that motion could stir the metal and generate electric currents. In 2011, researchers, including scientists working with data from NASA, proposed that mechanical stirring from Earth's gravity might have powered the lunar dynamo. This is different from Earth's dynamo, which is mostly powered by thermal convection. In the Moon's case, the energy source might have been mechanical rather than purely thermal. Another idea involves what scientists call precession. Precession is a slow change in the orientation of a rotating body's axis. Because the Moon is locked to Earth, gravitational torques can cause its rotation axis to wobble over long periods. That wobbling could transfer energy into the liquid core, driving motion. Computer simulations show that under certain conditions, this kind of mechanical forcing could produce a magnetic field strong enough to match what is recorded in ancient lunar rocks. But there is a problem. Models suggest that tidal stirring would weaken over time as the Moon moved farther from Earth. This matches the rock record. Strong magnetization appears in rocks older than about 3.5 billion years. After that, the magnetic signals become weaker. By around 1 billion years ago, evidence suggests that the lunar dynamo had mostly stopped. This timeline fits the idea that tidal energy decreased as distance increased. However, tidal models alone may not fully explain the strongest magnetic signatures found in some samples. That leads to another possibility. Maybe the early Moon was hotter than we think. Radioactive elements such as uranium, thorium, and potassium release heat as they decay. If the Moon had a higher concentration of these elements in its interior, the heat could have helped maintain convection in the core. The distribution of radioactive elements on the lunar surface is not uniform. Data from orbiters like Lunar Prospector revealed regions rich in radioactive materials, especially on the near side. These regions are associated with volcanic activity and large lava plains. This uneven heating may have affected how heat flowed from the interior. Scientists are still debating whether thermal convection alone could have powered the early dynamo, or whether it needed help from tidal forces. Some models combine both effects. In these combined models, early strong convection created a powerful magnetic field. Later, as the Moon cooled, tidal forces continued to stir the remaining liquid core, extending the dynamo's life but at lower strength. The story becomes even more interesting when we consider impact events. The Moon's surface is covered with craters from asteroid and comet impacts. Large impacts release tremendous energy. Some researchers suggest that giant impacts could temporarily enhance core motion or generate short-lived magnetic fields through plasma interactions. However, impact-generated fields would likely be local and short-lived. The widespread magnetization in some ancient rocks suggests a more global and sustained field. Today, the Moon has no global magnetic shield like Earth. The solar wind flows directly onto its surface. But orbiting spacecraft have detected small magnetic swirls on the surface, such as those associated with bright features called lunar swirls. These swirls may be linked to localized magnetic fields preserved in the crust. They are reminders of an ancient time when the Moon's interior was active. The Moon's magnetic field mystery connects many fields of science, including planetary formation, geophysics, orbital mechanics, and plasma physics. It forces scientists to rethink assumptions about small planetary bodies. If the Moon once had a strong magnetic field, what about other small worlds? Do they also have hidden magnetic histories? As technology improved, scientists began to re-examine the Moon's magnetic story with greater precision. The lunar samples brought back by the Apollo program were studied again using modern instruments far more sensitive than those available in the 1970s. These tools can detect extremely tiny magnetic signals, down to levels that were once impossible to measure. Researchers carefully selected samples that were least altered by impacts or contamination. They reheated tiny pieces of rock in controlled laboratory conditions to see how their magnetization changed, allowing them to estimate the strength of the magnetic field present when the rocks originally cooled billions of years ago. The results confirmed something remarkable. Around 4.2 to 3.5 billion years ago, the Moon likely had a magnetic field that may have reached strengths of 20 to 50 microteslas, similar to Earth's present field. But after about 3 billion years ago, the field weakened dramatically. By roughly 1 to 1.5 billion years ago, it appears to have faded almost completely. This timeline supports the idea of a two-phase dynamo. In the early phase, strong energy sources drove a powerful field. In a later phase, weaker mechanical energy, possibly from tidal interactions with Earth, sustained a reduced magnetic field before it finally shut down. At the same time, spacecraft orbiting the Moon provided new global maps of magnetic anomalies. Missions such as Lunar Prospector and later orbiters measured variations in magnetic intensity across the lunar surface. They discovered that the strongest crustal magnetic fields are not located in the largest impact basins, as some earlier theories predicted. Instead, many strong magnetic regions are found on the far side of the Moon, especially opposite the huge Imbrium basin. This strange pattern led to a new hypothesis. When a massive asteroid struck the Moon and formed a basin like Imbrium, shock waves traveled through the Moon's interior and converged on the opposite side. This focusing of energy could have altered crustal rocks and possibly enhanced their ability to record magnetic fields that already existed. In other words, impacts may have modified how magnetism was recorded, but not necessarily created the magnetic field itself. Meanwhile, computer simulations became more powerful. Scientists built detailed models of the Moon's interior, including its core size, composition, temperature, and rotation. Data from lunar laser ranging experiments, using reflectors left by astronauts during missions like Apollo 11, helped refine our understanding of the Moon's internal structure. Small variations in the Moon's rotation reveal clues about whether part of its core is still molten today. Evidence suggests that the Moon has a partially liquid outer core surrounding a solid inner core. Even though this liquid layer is small, it shows that the Moon is not entirely frozen inside. Some models suggest that early in its history, the Moon's core may have crystallized slowly from the inside outward. As iron solidified, lighter elements would have been released into the remaining liquid. This chemical separation can drive convection, a process similar to what helps power Earth's dynamo today. This is called compositional convection. It does not rely only on heat, but also on changes in material density during solidification. If this process occurred early and strongly enough, It could explain the intense magnetic field recorded in ancient rocks. Another line of evidence comes from the study of lunar meteorites. These are pieces of the moon that were blasted into space by impacts and later landed on Earth. Because they come from random locations on the moon, they provide information beyond the limited landing sites of the Apollo missions. Some lunar meteorites also show signs of ancient magnetization, supporting the idea that the magnetic field was global rather than local. Scientists are also comparing the moon's magnetic history to that of other bodies. Mars, for example, shows strong crustal magnetization in its southern hemisphere, suggesting it once had a global magnetic field that later disappeared. Data from missions like Mars Global Surveyor revealed these patterns. Comparing Mars and the moon helps scientists understand how size, composition, and cooling rates affect magnetic evolution. The moon is smaller than Mars, yet evidence suggests it sustained a dynamo for hundreds of millions, possibly over 1 billion years. That challenges simple assumptions about planetary cooling. Today, new missions are preparing to return humans and instruments to the moon. Through the Artemis program, scientists hope to place advanced geophysical instruments on the surface, including improved seismometers and heat flow probes. These tools could measure the moon's internal temperature and structure with greater accuracy than ever before. Future sample return missions may collect rocks from regions never explored before, especially from the far side where strong magnetic anomalies exist. By studying fresh samples from these regions, scientists may better understand how and when the lunar dynamo operated. There is also interest in placing magnetometers directly on the lunar surface for long-term monitoring. Although the moon no longer has a global magnetic field, studying how it interacts with the solar wind can reveal information about its internal conductivity. Every new measurement adds another piece to the puzzle. The moon's magnetic field mystery reminds us that even our closest neighbor still holds deep secrets. What once seemed like a simple, dead world now appears more complex. Billions of years ago, beneath its quiet gray surface, molten metal may have flowed inside its core, generating a magnetic shield that protected its surface from solar radiation. Over time, as the moon cooled and drifted farther from Earth, that internal engine slowed and finally stopped. Today, only faint magnetic traces remain locked in ancient rocks, silent records of a dynamic past. The mystery is not fully solved, but each mission, each experiment, and each new model brings us closer to understanding how a small world briefly powered a magnetic heart. The story of the moon's ancient magnetic field is not only about the moon itself. It changes how scientists think about planets, moons, and even the conditions needed for life. For many years, researchers believed that only large planets like Earth could maintain strong magnetic fields for long periods of time. A magnetic field was seen as a sign of a large, hot, and active interior. The moon seemed too small, too cold, and too simple to fit that picture. But the evidence collected from the Apollo program forced scientists to reconsider. If the moon, with its small core and slow rotation, could generate a magnetic field similar in strength to Earth's for hundreds of millions of years, then size alone is not the only factor that matters. Energy sources, orbital interactions, internal chemistry, and cooling history all play important roles. This realization affects how we study other worlds in our solar system. For example, the planet Mercury is small, even smaller than Mars, yet it has a weak but active magnetic field today. Data from missions like Messenger showed that Mercury's magnetic field is global but much weaker than Earth's. Scientists once thought Mercury's core should have cooled and solidified long ago. But the presence of a magnetic field means that at least part of its core remains liquid and moving. The moon's history shows that even small bodies can surprise us. The same lesson applies to icy moons orbiting giant planets. Moons such as Europa and Ganymede orbit Jupiter, and Ganymede actually has its own magnetic field. Observations from the Galileo confirmed this discovery. Ganymede is larger than the moon, but it is still much smaller than Earth. Its magnetic field suggests that internal oceans, salty layers, or metallic cores can create complex magnetic behavior. The moon's magnetic mystery helps scientists build better models to understand these distant worlds. Another important connection is the link between magnetic fields and habitability. On Earth, our magnetic field shields the atmosphere from being stripped away by the solar wind. Without this protection, charged particles from the sun could slowly erode the atmosphere and increase radiation at the surface. Mars provides an example of what can happen without a strong global magnetic field. Data from orbiters have shown that much of Mars' early atmosphere was likely lost over time. The Moon, however, never had a thick atmosphere to protect. Its gravity is too weak to hold one for long. But if it once had a magnetic field, it may have briefly reduced surface radiation levels. Some scientists wonder whether the early magnetic shield influenced how volatile materials, such as water, were retained or lost. Although the Moon is not considered a place where life developed naturally, understanding its magnetic past helps scientists think about how magnetic fields affect planetary environments in general. The Moon also serves as a natural laboratory. Because it has no weather, no plate tectonics, and very little erosion, its rocks preserve ancient records better than most places on Earth. Earth's surface is constantly changing. Old rocks are recycled by tectonic processes. On the Moon, however, rocks that formed billions of years ago can remain near the surface almost unchanged. This makes the Moon a time capsule of early solar system history. By studying the magnetic signatures locked in lunar rocks, scientists gain insight not only into the Moon's core, but also into the early environment of the inner solar system. One ongoing debate involves the exact mechanism that powered the strongest early magnetic phase. Some researchers argue that thermal convection combined with core crystallization is enough. Others believe that strong tidal forces from Earth, when a moon was much closer, provided additional energy. The Moon is gradually moving away from Earth due to tidal interactions. Measurements made using laser reflectors placed during missions like Apollo 17 show this outward drift clearly. Billions of years ago, when the Moon orbited much closer, Earth would have appeared much larger in the lunar sky, and gravitational forces would have been far stronger. That early closeness may have played a key role in powering the dynamo. Computer simulations continue to test these ideas. By adjusting parameters such as core size, temperature, rotation speed, and orbital distance, scientists can model different scenarios. These models must match the magnetic strength recorded in rocks and also match the timeline of when the field appeared and disappeared. The best models suggest a combination of processes. Early in its history, the Moon likely had enough internal heat to drive strong convection in its liquid core. As it cooled, that heat-driven dynamo weakened. Later, tidal stirring may have extended the dynamo's life at lower intensity before it finally shut down completely. Today, the Moon does not generate a global magnetic field, but it still interacts with the sun in interesting ways. When the solar wind strikes the lunar surface, it implants charged particles into the soil. In areas where local magnetic fields remain in the crust, these particles are partially deflected, creating bright swirling patterns known as lunar swirls. These features are visible in high-resolution images and are associated with magnetic anomalies mapped by orbiters, such as Lunar Prospector. These swirls may represent the final visible traces of a once powerful magnetic system. As humanity prepares to return to the Moon through the Artemis program, new instruments will allow scientists to measure the Moon's magnetic environment with greater precision than ever before. Future astronauts may deploy advanced magnetometers, drill deeper core samples, and place new seismic networks across the surface. Each new dataset will refine our understanding of the Moon's interior. The Moon's magnetic field mystery teaches a powerful lesson. Worlds that appear quiet and inactive today may have once been dynamic and energetic. Beneath the Moon's calm gray surface lies a story of molten metal, gravitational forces, and a magnetic shield that flickered for hundreds of millions of years before fading into silence. What we see now is only the final chapter. The rocks remember the rest. Even after decades of research, the moon's magnetic field mystery is not completely solved. Scientists agree that the moon once had a magnetic field. They agree that it was strongest more than 3.5 billion years ago and that it faded over time. They agree that the field was likely global, not just local. But the exact details of how it started, how strong it truly was, and exactly how it ended are still being studied. One major question is the true strength of the earliest lunar magnetic field. Some laboratory studies of Apollo samples suggest extremely strong values, possibly comparable to or even approaching the strength of Earth's present field. Other studies argue that certain samples may have been altered by impacts or later heating events, which could change the recorded signal. Scientists must carefully separate original magnetization from later overprints. This requires extremely controlled laboratory work, using shielding to block Earth's magnetic field, and using sensitive magnetometers that can measure signals billions of times weaker than a refrigerator magnet. Another open question involves the structure of the moon's core. Data from seismometers left behind during the Apollo program provided the first clues that the moon has a layered interior. More recent analysis suggests the moon likely has a solid inner core and a liquid outer core, somewhat similar in structure to Earth, but much smaller. However, the exact size, composition, and temperature of these layers are still uncertain. Even small changes in these values can significantly affect dynamo models. If the core contains lighter elements, such as sulfur or carbon mixed with iron, this could lower the melting point and allow liquid metal to remain for longer periods of time. That would make it easier to sustain convection and magnetic activity. Scientists are also studying how the moon's rotation changed over time. Early in its history, the moon may not have been perfectly locked to Earth as it is today. If its rotation rate was slightly different, or if it experienced stronger wobbling, motion that could have increased energy transfer into the core. The idea that tidal forces from Earth helped power the dynamo remains one of the most intriguing explanations. When the moon was much closer to Earth, gravitational interactions would have been intense. Earth would have appeared several times larger in the lunar sky. The constant pulling and stretching may have stirred the liquid core. As the moon slowly drifted outward, confirmed by laser ranging experiments using reflectors placed during missions such as Apollo 11, the tidal energy would have decreased. This matches the gradual weakening of the magnetic field recorded in rocks. Another important factor is the timing of volcanic activity on the moon. Large lava flows created the dark Maria that we see from Earth. These volcanic events occurred mostly between about 3.8 and 3 billion years ago. Many magnetized samples come from these basalt flows. If the dynamo was still active during major volcanic periods, then the cooling lava would naturally record the magnetic field. But volcanic activity declined over time, just as magnetic evidence weakened. Understanding whether volcanic heat and core heat were connected could help explain the timeline. Modern spacecraft continue to add new information. Orbiters have mapped gravitational variations, surface chemistry, and magnetic anomalies in high detail. Missions led by NASA and other international space agencies are building a clearer picture of the moon's internal structure. For example, precise tracking of spacecraft motion reveals tiny variations in the moon's gravity field, which reflect differences in internal density. These measurements help estimate the size of the core and the thickness of the mantle. Future missions planned under the Artemis program aim to return humans to the lunar surface and establish a more permanent scientific presence. New generations of instruments could be placed far from the original Apollo landing sites, including on the far side of the moon where strong magnetic anomalies have been detected. By collecting samples directly from these regions, scientists may determine whether those crustal magnetic fields formed in the presence of a global dynamo or were enhanced by large impact events. There's also interest in drilling deeper into the lunar crust. Most Apollo samples came from the surface or shallow depths. Deeper drilling could reveal older materials that record even earlier magnetic conditions, possibly closer to the time of the moon's formation. Such samples could test whether the dynamo began almost immediately after the moon formed from the giant impact, or whether it took hundreds of millions of years for the internal engine to develop. The moon's magnetic field mystery also helps scientists design missions to other worlds. When spacecraft measure magnetic fields around asteroids, dwarf planets, or icy moons, researchers now know that even small bodies can have complex magnetic histories. Lessons learned from a moon guide how instruments are built and how data are interpreted. In a broader sense, the moon reminds us that planetary evolution is not simple. A world that appears quiet today may once have had a dynamic interior, flowing metal, volcanic eruptions, and a protective magnetic shield. The moon we see now is only the final stage of a long transformation. Its surface is covered in craters and dust, silent and still. But inside its rocks is a record of motion, heat, and magnetism from a time when its core was alive with energy. Billions of years ago, deep beneath the surface, molten iron may have moved in slow, powerful currents, generating invisible magnetic lines that extended into space. That field eventually faded as the interior cooled and tidal forces weakened. What remains are faint magnetic traces locked in ancient stones, waiting to be read by careful instruments and patient scientists. The mystery is closer to being solved than ever before.